Hello students, in this video we'll discuss about recursive and recursive enumerable languages. Simply the languages accepted by the Turing machine. So in the last video we have discussed about Turing machine as enumerator. Coming to this, what are the languages accepted by the Turing machine? See, even though it is restricted or enumerated or modified Turing machine, so the languages accepted by the Turing machine only two types. One is recursive language and another one is recursive enumerable language. And when we can call it as recursive language and when we can call it as recursive enumerable, before going to that, let me tell you the halting problem of Turing machine. Right. So as we have already discussed in the previous videos that see, if you write a Turing machine or if you construct a Turing machine, so for all the inputs, the Turing machine should be altered or terminated, we can say that. Whether the input is accepted or rejected, but the Turing machine must be terminated or altered for every input string. So if such, we can say that those languages are recursive languages. Then when it comes to that, if you construct a Turing machine for any language, and for some inputs it is going to accept, for some inputs it is going to reject, and in both the cases it would be halted, but for some inputs that may enter into the infinite looping. So here we can say that there is a halting problem for some inputs, so those languages are called as recursive enumerable language. So we can construct a Turing machine with two things, one with the halting and another one without halting. So then if there is no halting, then how can we accept it? We have to reach the final state, then we can accept it. And if there is halting, you don't need to worry about the acceptance also. If the Turing machine altered, we can decide whether the string is accepted or rejected. Okay. So there are two ways to accept the Turing machine or the languages. One way is defining the final state. As usual, we have discussed for the finite automata, push down automata, like you take a string such that from the starting state, and if you read that input string, taking all IDs, then at the end it has to reach the final state. Then we can say that the set of all strings which are accepted by the Turing machine is the language accepted by the Turing machine. Or sometimes we can even construct a Turing machine that accepts a language simply by halting. You no need to worry about the final state here. In that, what does it mean here? See, you have to take all the strings starting from the Q0 and read all the strings with the IDs, whatever the IDs we have specified. And after reading all the input symbols, if there are no possible moves from that ID, means if there are no possible moves, for example, you have stated here like AXR, something like we are taking here B, A, pop, something, okay, sorry, B, Y, left, like that. So we are having here again Y, Y, L, something, right? So delta, delta, right? You can say that this is a state. Now, if it is a final, okay, well and good. You have reached this state, and if there are no possible movements, then we can say that the Turing machine will be altered. There is no questioning of going into infinite loop. And what is the input you find right on the tape? That would be the string accepted by our finite Turing machine. You don't need to worry about the final state. So if there are no possible moves here or whatever the state, for example, here we are having A and B. What if I reach an X here? Assume that this is Q0. So if I get a statement like this, Q0 X, or what is it? Where should I go? There is no movement. So the Turing machine halted here. And whatever we are having on the tape, that is a string we are expecting from the Turing machine. Got my point, right? So this is how we are going to accept the languages, right? So same, we can convert the Turing machine with halting to accepting, and we can convert the accepting to Turing machine halting also. So let me go with the two statements here. If there is a language accepted by the Turing machine with the accepting, then there must exist a halting of the Turing machine for the same language. Right? If you are having a accepting for some language L, then there must be some modified or as usual Turing machine for the halting also. In the same way, if there is a language which is accepted by the halting of the Turing machine, then definitely there exists some Turing machine with the modified as it is for that accepting by the final state. Simply we are saying that if it is a language is accepted by the acceptance must be converted to halting. If a language is accepted by the halting must be converted to acceptance. Both are possible. We'll go with that. How we can do that, right? Assume that guys we have a let me go with the first one, acceptance to halting. Assume that we have a Turing machine with the acceptance like this. So q naught 0 1 we are going right side, okay, then delta delta, let me go with the ones complement, for example 1 0 right side, and we have a acceptance state here like this. Then how can we convert this accepting state, right, to the final state? Okay, then sorry, accepting state to the halting machine. Then what you have to do, first step, you have to introduce a new state s, right? So for each accepting state M, remove any moves. So if you have any moves from this final state, just remove it. Of course, we don't have any here. Then you can go for it. 1 0 R or 0 1 R, then delta delta N, and don't make this as a final state. Then if you have any moves on this final state, just remove it. Okay, then you may get it out. Sir, what if I have a 2's complement like this L, then 0 1 left side or 1 0 something? Okay, if you have some movements, forget about it what we are doing. If you have such, what we have to do, then you may get it out, right? So first you have to remove it, but removal of that will change the language, right? Then what we can do here, so change it to introduce a new final state or new state S, to not stop here, then take all the movements as it is 0 1 1 0 left and something. Then for this earlier final state to the new final state, make all the input symbols like 1 0 R and delta delta N, like, or sorry, 1 0 L 0 1 L, like that. Whatever the movements we have here, okay, 1 0 L 0 1 L, whatever the movements for all the input symbols, just you take into the a new state, so that you read how many you want here, and if you want to halt, you can come back to the S and you can halt here. That's how it is going to be. So here we are saying that to avoid M accidentally halt, then introduce a new state S, which runs on the right forever. So it always goes to the right only, so that the new state S of X is leading S XR. So it is going to, you have to take the movements of all the input symbols which will go to the yes, right? Then you may get it out. Sir, what if there is a state which is not accepting it? How can you say that? Right? If you want to say that the strings are not going to be accepted, just don't give any movement for it, right? Undefined. Now, for example, if you are saying that for all the input symbols you are giving, let me convert the same thing, 0 1 R 1 0 R. Then earlier we are having here delta delta N. Okay, that was the final state earlier. Then I'm introducing a new state S, right? And it keeps on moving right hand side. If you have anything here, right, then we have to take whatever the movements earlier we are having. So 1 0 L 0 1 L, like that you can take it, and it has to reach the state. Then how can I say that it is not accepted? Means you should not define any movements here, right? If you define it, then this is going to be halted, and we can say that it is accepted, right? Or 0 1 L, halting means we are saying that accepting. Then how can you say that it is rejected? Means you should not define such movements. For example, you are saying that for 0 it should not accept it, means then don't give this movement. If you don't give this, then we can say that that is not going to be accepted. If there is no particular movement, that is not accepted, right? So let me go with the conversion of halting to acceptance. Assume that we have a Turing machine with only halting, like this 0 1 something. Okay, forget about what I'm writing here. So just go with the movements only. So delta delta no movement, and we are saying that As we don't have any movements here, then we can say that it will be halted here. But how can we convert into the acceptance? Just create a new state f, which is going to be accept, and f should not have any movement here. Then whatever the movements you have for the delta n here, just repeat it again for this new state. Okay, so you can write here delta n, or you can say that epsilon n. You can take it. So when you come to this state, we can say that it is accepted. You write whatever the depends on the language. For example, if you are having some other symbols of that, for example, 2's complement, after performing the 2's complement by going to the left side, you'll be having the remaining symbols. You'll find the one, right? For example, 0 1 0 1. Okay? Then 2's complement, 1's complement will give you 1 0 1 0, delta will come here and will change this 1 to 0. Then again you have to, if it is halting, you can accept here only by not going anywhere. But if it is final state, then you have to move right side by reading the 1 delta that you have to specify. So this is not constant here, depends on the language. You can go with whatever you want. And go with this recursively enumerable languages. As I told you, there are languages accepted by the final state and the halting. So recursive enumerable languages mean there is a possibility of going to the infinite loop, right? So for some language, for some input string, not for all, we have already discussed, right? So then if there is a possibility of going to the infinite loop, then we can say that it is recursively enumerable language, right? If it goes to the infinite loop or not, we can accept the strings. There is no problem with that, right? So coming to the recursive language, so definitely it should be altered, right? Or it should be accepted. Two things should be done, whether it has to be altered and somewhere some input, or it is not altered means acceptance, or it should not accept the string, we should reject it. There are only two possible ways, right? So in such cases we can say that that is a recursive language. If we have three possibilities, recursive enumerable, two possibilities, recursive language, right? So examples, see, we have like this, every CFL is a recursive language. We have an hierarchy like this: regular languages, CFL languages, and CSL languages, and recursive languages, and recursive enumerable language. This we will discuss in the next videos, the hierarchy. So everything, almost everything is recursive language. Only when there is a looping chance, then only it is not a recursive language. It is only recursive enumerable language. So then we have some properties for the recursive languages and recursive enumerable. Just go through with this. We have already given the proofs for this closure properties of regular languages and CFL. We can apply the same thing. Whatever we have taken for the CFL and regular, even you can apply the same thing. Like, what does it mean? Intersection here, right? So recursive languages, how can we read it? Recursive languages are closed under intersection. Recursive languages are closed under intersection. Right here, the recursive languages are not closed under homomorphism. Same way, recursive enumerable languages are closed under intersection, not closed under complement. What does it mean? We have already discussed about this. If L1 is recursive language and L2 is recursive languages, if you are saying that the closed under intersection, L1 intersection L2 must be recursive language. That's the meaning of it. What about this not closed under? See, if L1, L is a recursive enumerable language, then recursive enumerable languages are not closed under complement, means the L complement may or may not be recursive enumerable language, may or may not be. We cannot give a conclusion. Right? So this is about recursive languages and recursive enumerable languages. So the next video will discuss about universal Turing machine and undecidable problems.